but I usually go by look. Okay, recording. Okay, I usually go by look, and I'm going to give a short self introduction here. I'm currently a senior undergraduate in Peking University, China, and I'm going to start my PhD studies in Stanford in next fall. Yeah, and my major is computer science. I have participated in the informatics in Olympiad in China. So yeah, so I'm glad to have the opportunity to share my experience with you. Okay, so before I begin, I just want to remind you that you're welcome to interrupt at any time if you have any questions. Just feel free to ask, or if you feel uncomfortable to unmute, you can just send the questions in the chat, and I'll manage to see the chats and answer the questions. Okay, so I guess we'll begin. Today, we're going to cover the three problems from USACO 2022 February contest silver. Okay, let's begin. So the first problem is called redistributing gifts. I'm not sure if you have tried this problem before, but I'll start assuming that you haven't even looked into them. So it's basically like there are n calls and n gifts. Okay, so the number of calls equals the number of gifts, and each call has a wish list. That means a wish list is a permutation of n gifts, and in a wish list is like for example, call 1 has a wish list, for example, 2, 3, or 1. So that means call I likes gift 2 first, the most, and then comes gift 3, and it likes or he likes gift 1 the least. Okay. So here we define what is an valid assignment of gifts. Okay, so you have n gifts you want to assign to n calls, but there are some restrictions. So we want the assignment to be like for each call I. If call I receives gift j, then either j is equal to I, or call I prefers gift j over I. That means each call receives a gift that is better than the gift with the same number as itself. Okay. Or there's another way to view this, like in the original USACO problem statement. That is, originally we assign call I with gift I. Okay, so call 1 get gift 1, call 2 get gift 2, and so forth. And then we redistributed the gift, and we want each call to be happy, like they get a better gift than before. Okay, yeah. So we're considering all the valid assignments. We want to know for each call, what is his most preferred gift that it can have. Okay, just from this text, it may be not easy to understand. So I made some animation and example input output. So let's take a look. Because the USACO official solution does not contain like visual elements or like pictures, so I've added some here and hope this helps. So here we have 4 calls, and each call has a wish list, like we said before. So call I's wish list is 1, 2, 3, 4. Call 2, 1, 3, 2, 4, and call 3 1 2 3 4, call 4 1 2 3 4. That means this gift 1 is preferred most by all the calls. Okay, so let's see. So now we have because we have defined what a valid assignment is. So let's say for an valid assignment, each call which gifts can be distributed to each call. Okay, so so for call I, it can only receive this gift 1. Okay, because gift 1 is this call's most preferred gift, so it has not other choices. And for call 2, we first find where 2 is in the this wish list, and then either this gift 2 or the gifts before it, like 1, 3, 2. These 3 gifts can be distributed to call 2. Okay. And for call 3, similarly is 1, 2, 3. And for call 4 is 1, 2, 3, 4. So that means this gifts I have colored in red. It means the gifts that we can give, we can redistribute to this call. So let's see what best gifts can each call have, or what most preferred gifts can each call have, which is the output that we should compute for this problem. So for call I, there is not much to say, right? Because it can only have gift 1, so the most preferred gifts in all valid assignments is just gift 1. So let me, so I have colored in blue valid assignment that makes call 1 have this gift 1. So it's just assign for each call I, assign gift I to it directly. Okay, so call 1 get gift 1, call 2 get gift 2, call 3 get gift 3, and call 4 had gift 4. But if we look at what call 2 can have, it's a little bit more interesting. Because so in the last assignment, we see that call 2 have gift 2, but it remains a problem whether it can have better like gift 3 or gift 1. But it's clear that call 2 cannot have gift 1, right? Because in all the valid assignments, call 1 must have already have gift 1. So yeah, so let's try gift 3 instead. And we found one possible assignment like this, right? Note that for each call, the assignment that we found may not be the same. Okay. Yeah, and so this call 2 have gift 3, and we just exchange the gifts between call 2 and the call 3. Then we have that the call 3 have gift 3, and that's the most preferred gift that this call 2 can have. And also for call 3, it's also true that it's the same assignment that makes it get his most preferred gifts. That is this gift 2. Yeah, and it's similar. And for call 4, it's a bit tricky, right? Because though it can have all the 4 gifts, but we have seen that first call 1 must have this gift 1. So gift 1 is distributed already, and for call 2 and call 3, they must choose from 2 and 3. So gift 2 and gift 3 by this time have also been distributed to call 2 and call 3. So call 4 can only have gift 4. Okay, so for this problem now, what our output would be 1, 3, 2, 4, right? Because that's the most preferred gift each call can have in all valid assignments. Okay, so this is our sample input and output. So how should we solve this problem? Well, the solution here I will cover is also from the official USACO solution, but similarly, since the USACO solution only shows the text and it only shows the final solution without any initial intuitions, like how should we come up with this idea. So I'll try to have some intuition here. So okay. So the first intuition when I saw this problem is that there is a complex relation between the calls and the gifts, right? So we can see that for each call, there are only a number of gifts that this call can have. Okay, so for me, it's quite natural to represent this complex relation with a graph. Okay, so also very naturally, in a graph, we just model each element in the problem with a vertex, and the relation we model them with with edges. So okay, so following this intuition, we now construct such a graph that each call is a vertex, and each gift is also a vertex. And we connect a call to a gift if the call can have the gift in a valid assignment. Okay. So here we can see that call I can only have gift i's. Call 1 can only have gift 1. So there's only one edge connecting call I to gift call 1 to gift 1. And similarly, there are 3 edges for call 2 and call 3. And there are 4 edges for call 4. Okay. Yeah, and we can see that this is a bipartite graph, but this property will not come in handy in this problem. Okay, so now each call can choose the gift with its same number. Okay, so like call I can choose gift I. We can view the problem as we said originally that for each call I, it originally have gift I, and then they can exchange their gifts so that everyone is happy, everyone gets better. So here we can try to dig deeper into this graph and see what does a loop represent in this graph. For example, I have colored in red such a loop from call 2 to gift 2, and from gift 2 to gift to call 3, and from call 3 to gift 3, and then from gift 3 to call 2. It's quite obvious, in my opinion, that since each edge represents that one call can have one gift. Okay, so here if we have a loop, then let's say call 2 can have gift 3. Okay, and gift 3 is originally owned by call 3, and call 3 can have gift 2, and gift 2 is originally owned by call 2. So seems like a loop like this represents an exchange, kind of a valid exchange plan. Okay, so we can see from this loop that we can exchange the gifts of call 2 and call j. Okay, in a valid assignments. Yeah, and so if we look at like call 1. There's no loops connecting that contains call 1. So that means this call 1 can only have its original gift, that is gift 1, and there's no exchange that can happen to let call I get call 1 get other gifts. So but the previous graph may seem a bit complex. And actually, there is a way to reduce it. So this is actually a general trick, and I can so first introduce it to you briefly. So it's like in this graph, since we can see that we only care about loops, we don't care about like the length or the path length. Okay, so that means we can reduce some vertices to one vertex together if they have been connected. Okay, so so right now we have seen that since each call I can have its original gift or have gift I, so there's an edge between call I and gift I, and that means these two are always connected. And so from this general rule, we can reduce them into one vertex. Okay, so we combine the call I and the gift I to one vertex, and now we get a simpler graph. Similarly, like since call 1 can only have gift 1, so it has a self loop, and call 2 and call 3 they have like gift 1, 2, 3, right? Remember, so they have 3 edges. Okay, like from call 3 from this node 3. It connects 1 and itself, and then gift call or gift 2. So now, what does a loop represent? Again, well, similarly, for example, let's say there's a self loop that's the most simple, like that connecting vertex 1 and vertex 1. Okay, so this loop is quite simple. It just means that call 1 can have gift 1. Okay, and we can see a more complex one. So so for this loop, okay, it means call 3 can have gift 2, and call 2 can have gift 3. Okay, so that also, you know, it's similar that we have an exchange plan that can work. So whenever we find such a loop, it means for each node here, for each call in this loop, it can have all the gifts from this loop. Okay, so now we are seeing a loop with 2 vertices. So that means this call 2 can have gift 3, and this call 3 can have gift 2. But if there is a loop that contains 3 vertices, so for example, if there's some edge here, sorry. Let me draw something. It seems I cannot draw. All right, it's fine. Let's just assume that there's also an edge from this node 2, vertex 2 to vertex 4, and from vertex 3 to vertex 4. Then there will be a loop that contains this vertices 2, 3, and 4. And that means for each of these 3 calls, call 2, call 3, call 4, they can have the 3 gifts. Okay, in one assignment, they can have gift 2 or gift 3 or gift 4. Okay, so that's about the graph. So now, if we have this graph, it's quite straightforward. How should we then find the solutions? So first, we find all the loops, and then you know, because each loop, in each loop, we have seen that in each loop we can find, you know, what gifts for each call can have in all assignments. So we just iterate the wish list one by one to see, like for the first gift, whether you are whether this gift is in this loop, or if not, we can find the next. Okay, so yeah, that's the solution for this problem. And let's say some code to get a better understanding. So finding all the loops is not that easy, like in the silver level, I believe, in this USACO Silver level. So there are actually two ways for doing this, find all the loops. The first one is just we start and DFS from each vertex, and since we so that we know that for each node, which node it can reach. Okay, for each node, it's all reachable nodes, and so if for example node I can reach node J, and there is a back edge from node J to node I, or in other words, node J can also reach node I. Then it means there is a loop between node I and node J, right? And in this case, we then know that call I can have gift J, and call J can have gift I. Okay, so here is basically the code that shows how do we find all the loops with this approach. So we first enumerate all the nodes, and we start DFS from these nodes. And here the first parameter is the source, and the second is like the current node that we are exploring. And yeah, this is just a basic DFS. So I'll move on. Did anyone see anything?
Yeah.
Hello?
Is this C++?
Yeah, this is C++. Okay, yeah. So yeah, the code I show like in the slides are all C++, because I guess C++ is quite a popular language like in this programming context, right? Okay. But if you prefer other languages, please let me know. I can later like show other languages as well. But there is another more straightforward, or if you know the Floyd algorithm, Floyd-Warshall algorithm, you can just do a Floyd algorithm, and then you know all the reachabilities between each pair of nodes. Okay, and yeah, and so here we don't the standard Floyd algorithm computes the the path, the shortest path between each two nodes, right? But here we don't care about the path length, we only care about reachabilities. But that's similar because if there is a path that is that is not like an infinity, with length infinity, then it means there is a these two nodes can reach each other. Okay, so yeah, this is all similar. So which of these two approaches are better in time complexity? Well, let's say that for a DFS, the complexity is O(n plus m), right? If you are familiar, like n is the number of nodes and m is the number of edges in the graph. Okay, so but in this problem, we have seen that m is actually O(n squared), because like each call can have all the gifts. Each call in theory it can have all the gifts. So each node can have like n outward edges. So the m is O(n squared). And so for each DFS, the complexity is O(n squared), and there are n nodes. So the complexity in total is n times n squared. So it's like O(n) n to 3. Okay, or yeah, or n cube. And so this Floyd, we know that Floyd algorithm, there's 3 loops. So it's also like n cube. So they are actually the same complexity. Now with the reachabilities that we have computed, we now only need to iterate the wish list for each call. Okay, and find the first call, find the first gift that in the wish list that will, this call can have, and print it. That's all. And so you can see that this is there is a break because we only print the first one. So let me summarize the solution and the complexity. So first, we find all the loops. Now, first, of course, we need to construct a graph. Okay, but that's quite straightforward. So after that, we find all the loops, and we either DFS from each vertex, or we use Floyd algorithm, and then we iterate the wish list for each call, and the total complexity is n cube, and which is sufficient to like n well 500-ish n. Okay. Okay, so that's all about the first problem. Because it's the first problem, so I spent a little bit more time, and I'll try to go a bit faster, like in the later problems. Actually, they are a bit easier than the first problem, in my opinion. Okay. Okay, so this problem 2 is also a bit complex, but the last problem is a bit easier. So for this problem 2, it's called robot instructions, and actually it's like you are given n instructions, or in my opinion, n vectors, or say like xi and yi, which moves a robot x unit right and y units up. Okay, and here n is less than or equal to 40. And you are given a destination that you want to, and you want to move your robot from this 0, 0 to this xg, yg. That's the destination. Okay, but so here we want to know that we want to know all the possible instruction sets, right? Or at least the count of them, how many there are. So we want to know for each k from 1 to n, the number of ways to use only k instructions, and each instruction at least once to move the robot from 0, 0 to the destination. Okay, so it's like you choose k instructions from the whole n instruction set, and all the x, y mentioned above are in range minus 10 to 9 to 10 to 9. Okay, so as usual, let me first introduce you with an example with some figures, so help you better understanding the problem. So now suppose we have only 3 instructions, like 1, 0, 1, 1, and 2, 1. And the destination is just 2, 1 here. So this is 0, 0. Okay, so how should we move our robot to 2, 1? Well, obviously, there's one way to use one instruction, just use this 2, 1, okay? And it will directly move to the destination in one step. And second, we can use 2 instructions. The first 2 instructions here. So that first move the use this 1, 1 instruction to move it to the destination. Okay. Yeah. So this is the second way to do that. Use 2 instructions, and this is the way to do it, like in just 1 instruction. Okay. So let's go back to our problem statement. Intuitively, like when I saw this problem first, I was thinking that a dynamic programming algorithm may help. I wonder if you see this problem the same way. Okay, because DP or dynamic programming is quite used often to for counting, or like counting the ways to do this, counting the ways to do that. And this problem wants us to output the number of ways for each k, okay? And to me, it's just intuitive to use some DP similarly as the knapsack problem, okay? I wonder if you are familiar with knapsack problem. Yeah, to me, this is just a two-dimensional knapsack problem, right? However, it's hard to use DP in this problem. Why? Because the key is here, like the XY mentioned above are in range like 10 to the 9. Okay, remember that if you do like knapsack problem dynamic programming, the array length should be the maximum weight, okay, or the and so here if we view this destination as kind of the weight that of your knapsack, then it's like 10 to the 9, and it will then your memory would blow, and you will have memory limit exceeded. Okay, so yeah, but a good news is that here n is only like less than or equal to 40. So maybe we can just use some search. Okay. Okay. So, but before we jump into the final solution, let me first introduce you with some simplified version of this problem. Okay. So let's say that first I reduce the two-dimensional problem to one-dimensional. Okay, so suppose that we are given n instructions xi, not xi yi, but only xi, and which moves a robot x unit right. Okay, and the destination also becomes one-dimensional. And another change that I made is to restrict the n to less than or equal to 20. Okay. So, but all the x are still in the range. So how should we do this problem? If you have any ideas, please send in the chat or just unmute. I'd like some interactions, but if not, it's also fine. I guess this is the first time we meet, so people may be a bit shy. I don't know. See in the chat. Yeah, I actually Zoham just Zoham just saw just said a quite interesting idea. Yeah, so for this problem, because n is less than or equal to 20, it's just so yeah, that means we can afford a bit mask DP, or more simply, we just enumerate all possible subsets of these n instructions. Okay, so how many subsets are there of these n instructions? Is 2 to the n, right? You should be familiar with kind of the like for each n, which complexity can you afford? Okay, so for n equals 20, usually if the problem requires like 1 second or 2 seconds of your program to finish, then if n is 20, then that means you can at most afford like 2 to the n complexity. And similarly, like the last problem we have n equals 500. And the 500 usually means that the algorithm should be like at most n cube. Okay, so that's actually some hint like in the program, in the problem that we can use. Okay, so for this n equals 20, well, we just use brute force. Okay, we just enumerate all the subsets of these n instructions. And after the enumeration, we just add up the sum for each combination or the subsets, and we know that for this subset of the instructions, can we move the robot to its destination? we just verify if the sum equals xg. Well, if it equals xg, then we have a valid subset, right? And then we just need to count. So that's quite straightforward. Okay. But well, let's say if n equals 40, like in the original problem. So in this simplified problem 2, we also have only one dimension, but I increased the n from 20 to 40. Then how should we do? If we still enumerate all the possible combinations or the subsets of the original like 40 instructions, then of course there will be you will have a time limit exceeded, because 2 to the 20 you can handle in like 1 second. 2 to the 20 times 2 to the 20, you have to handle it like in 2 to the 20 seconds, and that's I don't know how many years. Okay, so yeah, but how should we proceed? What if we can do like 2 to the 20 plus 2 to the 20 instead of 2 to the 20 multiplied by 2 to the 20? Okay, so yeah, let's first enumerate like all the subsets for the first 20 instructions, and also we enumerate the subsets for the last 20 instructions. So each enumeration have 2 to the 20 complexity, right? But now, if we want to, if we want this operation to be plus, not times, then we need to think hard about how should we combine these results in linear time. Okay. Actually, the trick that I will cover like next, like how should we do this plus instead of this multiplication. It has a name. This trick is commonly called like meeting the middle. And if you solve the problems like in code forces or some other like say the solutions in USACO, you will see this word because this is a common trick. Okay, so I'll introduce this meeting the middle trick to you. Okay, so let's see some examples. So here we have the same enumeration for the first 20 instructions and for the last 20 instructions. So now so now for each subset, essentially we have a tuple, okay, a tuple, and its first element is the sum of the instructions, in this subset, and the second element is the number of instructions in this subsets. Okay, and now let's say that for like the first 20 instructions, we have like 2 to the 20 tuples. Okay, and also for the second, we have 2 to the 20 tuples. Now suppose we sort them. We sort each array. So now like for the first 20 instructions, we have array of tuples, and for the second also an array of tuples. Suppose that for each of these two arrays, we first sort it by the sum or the first element. Okay. Now what we have. So let me first introduce you with an example. So here, suppose for the first half of the instructions, we have this three tuples. That means 3 subsets that I have shown here. So okay, so here it means 32. It means there is a subset for the first half of the instructions that sum up to 3 and uses 2 instructions. And similarly, this 5-3 means that there is a subset of the first half of the instructions that uses 3 instructions to move the robot 5 units. Okay, and so in the second array is for the subsets of the last 20 instructions. So we can see that if we combine one subset in the first half of the instructions, with a subset like in the last half of the instructions, then we get a valid subset of all the instructions, right? And actually, it covers all the subsets of the whole instruction set. Okay, so let's go back to our original question. How should we combine them like in linear time? Okay, because if we combine for each tuple in the first array, we enumerate all the tuples in the next array, then it will be again 2 to the 20 times 2 to the 20. That's not what we want to happen. So how should we proceed? Well, there is a trick embedded in this meet in the middle, and that's called two pointers. Again, you can see like this two pointers mentioned quite often, like online for various problems. Okay, so let's say that now because we have stored these two arrays, and that means we can exploit this their order. Okay, so let's say because we only care about the subsets that move the robot to exactly xg, okay, not less, not more. We just need to move the robot to its destination. So okay, so let's say the xg is 10, okay, and for this 3, 2, how should we combine it with another with a subset of the last 20 instructions, so that after combining them, the robot will move to like 10. Okay, so obviously it should be combined with this 7, 3, right? And similarly, because 3 plus 7 equals 10. And similarly, this 5, 3 should be paired with this 5, 2, right? And this 8, 3 should be paired with 2, 1. So have you got any intuitions from this example? How should we combine the results in linear time? Since we have limited time, so I just proceed. So you can see that since we have sorted the arrays by sum. So for the instructions for the combinations or the tuples on the right of the first array, you should be paired with some subset or combinations or tuples on the right of the second array, right? So now we suppose that we have found such a match, okay? And now if we move the first, if we move the pointer in the first array a bit right, okay, one element right, so we move it to 5, 3. Where should we look for this 5, 3 match? Of course, we should look for it like by moving the pointer in the second array left, right? So that we can keep the sum of the the two sums sum up to this xg, right? Okay, so that's our algorithm. That's what two pointers do. We just move the first pointer from the first array right, and at the same time move the pointer from the second array left. Okay, so if we do this, we can find all the matches. But if you consider how many times we have moved the pointers, you see that in the first array, we just from beginning to end, we just move the pointer from its beginning to the end. And for the second array, the second pointer, we just move it to end, from end to begin. So in total, we only do like ON pointer movements. So the complexity is linear, okay? And that's the trick. So that's how we combine these two results in linear time. Okay, so that's all about this meet in the middle trick. And but the two pointers solution may not be necessary, because there's another way to do this. You can directly use hashing. Okay, So we don't need to sort them, but we only since for each tuple in the first array, we want to find this match in the second array, right? And what we need to do, we only need to like first subtract xg with the sum in the first array. For example, like the xg is 10 and the sum here is 5. So we get it's subtract 10 with 5, then we get 5. So we just need to find the 5 in the second array, right? Well, we can do a hashing, right? We can just insert all the elements in the second array into a hash table, and we find the we just do a hash table lookup, and that's enough. Because the hash table has an amortized ON insert or lookup complexity, it's also linear in time to do this combination. However, in reality, when you implement a hash table, or if you use some standard library in C++ that like unordered set or unordered map, they typically have a big constant. Okay, so so in practice, your program may run much lower than if you use the 2-pointer trick. So I'd personally recommend that you use the 2 pointers. It's not so hard. Yeah. Okay, so now we have the simplified version 2. Now we solve simplified version 2. So now it's time for us to get back to our full version, to the original version, and try to attack it. So now we can see that the full version has also like n is 40. So that hints us to use the meet it middle and the 2-pointer trick as well. And but the only difference is that the n instructions and the destination are 2-dimensional. Okay. Yeah, and actually there is not much a difference from this 2-dimensional to 1-dimensional. If we consider instead of in 1-dimensional, we just sort by the one sum, right? And now we sort by a tuple, like the x sum and the y sum. Okay, and yeah, it's actually similar. So let's say this example. So suppose we have 3 tuples for the first half of the instructions. Okay, 3, 4, 2. That means in this subsets of the first half of the instructions, x sum is 3 and the y sum is 4, and it uses 2 instructions. And we need to find a match to pair it and pair it with this match, and so that they sum up the x sum of these 2 tuples sum up to 10, like in this xg, and the y sum of these 2 tuples sum up to 10. So this match is this 7, 6, 3. Okay, and similarly for this 3, 5, 3 is match is this 7, 5, 2, and for this 8, 7, 3 is match is this 2, 3, 1. Okay, so similarly, if we sort by this tuple like x sum and y sum, that means you use x sum as the first k to compare. And if the 2 tuples have the equal x sum, then you compare the y sum. Okay, so if you sort by this, it's similar that if you move the first pointer from left to right, then you need to move the second pointer from right to left. So yeah, you just apply the same 2 pointers algorithm, and that's it. Okay, so that's all about the solutions for this program too. Similarly, I'll show you some like code snippet of the standard solution in C++, so that you can have a grasp of how should you write the program. So here is the meet it middle trick. Okay, so so this all subset it calculate like all the tuples that I have mentioned. Okay, so you can see that here is a pair of p and int, and the p is kind of a pair of x sum and y sum, just like in this slide. Okay, and this a, for this a vector a, you get like all the subsets, all the tuples for the first half of the instructions. You can see that is from begin to begin plus half of n, and similarly you have the part for the the next half. Okay, and so here is the code to combine them. There is some details about this implementation of two pointers, because if you consider that if two pointers, if two elements consecutively in the first array has the same, let's say has the same p or has the same x sum and y sum, then their matches are the same, right? And you should carefully correctly compute that. Okay, so because we have limited time for the final question, for final problem, so I'll not show more details about this code, but you can find this code like in the USACO website, official website. Okay. There's a question from Zoham. So he asked, what are my left and right pointers? Are they variables? Yeah, of course. You in your implementation in the program, you have to use something to store the pointers, right? So it can be like a variable that index to the array, or you can use like a pointer, just like a pointer in C or C++. Okay, so yeah, I actually since you have asked, I can show you like in this code, this IB actually, this IB, you should be able to see my mouse, right? This IB here, like in the 1, 2, 3, 4, 5, in the fifth line, is the pointer of the second array. Okay, and here since here this for loop, it enumerates all the elements of the first array. So conceptually there are two pointers. Okay, it's only like the first pointer is hidden in this for loop because you just enumerate it all one by one. Yeah, so since we only have limited time for the third problem, I'll move on. But you can find the details in this code. Okay, yeah, and feel free to ask me like after this class, and I will give you my email address like finally. Okay. So the final problem, I think, is a bit simpler than the first two problems. Okay, so it's called email filing. So let's say Farmer John has n folders on the left and n m folders on the left and n emails on the right on his screen. Okay, and for each email or let's say a file, it needs to be filed into a folder fi. Okay, so each email is assigned a folder, and but the screen size is limited, so it can only show like k folders and k emails on the screen at once. Okay, and another restriction is that you can only scroll down, either scroll down the folders so that the first folder go up and out of the screen, and the next folder show up at the bottom of the screen, or similarly you scroll down the emails on the right. And the problem is given the above parameters, you should decide whether it is possible to correctly file all the emails. Well, I find this text a bit hard to follow, right? I guess you must find the same. So again, let me show you some example. So let's say that there are four k equals 4, and that means we can have only 4 folders and 4 emails at the same time on the screen. So okay, so now this is our first 4 folders and the first 4 emails. And here f1 equals 6. That means this first email needs to be sent to folder 6. Okay, but folder 6 is not on the screen now, so we cannot file it right now. Okay, similarly, f2 is also 6, and f3 is 1, and f4 is 6. Well, we can see that only this f3, only this email 3 can be filed to folder 1 right now, right? Because all the folders on the screen are just 1, 2, 3, 4, not 6, 7. Okay, so let's move this let's file this third email to folder 1. Okay, and let's move on. Okay, so after we file this f3 to folder 1, it just this email disappears. Okay, and this fourth email goes up, and this fifth email goes up from the out of the screen to at the bottom of this screen. Okay, so so now we can see that all this f 6, 6, 7, 5, they are not on the screen, right? So we cannot file them incorrectly in their folders. So what can we do? We can scroll down the folders. Okay, so let's scroll down the folders, and then we have like 2, 3, 4, 5 folders on the right. Okay, and so now we can file this the fifth email to this the fifth folder. Okay, so after we file it, now we have this sixth email on the screen now, and the fifth email disappears because we have filed it. Okay, now all the emails on the screen needs to be filed into some folders not yet on screen. Okay, so similarly, we may think that okay, then let's just scroll down the folders, right? Like we did for the first folder. However, if we suppose that this seventh email that have not shown on the screen, it needs to be filed into this folder 2. Okay, now since we can only scroll down, not scroll up, if we scroll down the folders right now, the seventh email cannot ever find its the second folder later. So it's not possible that we scroll down the folders at this time, okay, because we'll lose folder 2 forever. So what should we do? Well, yeah, if we scroll down, folder 2 can never come back. So let's first skip the first email and scroll down the emails first. Now we have this first emails scrolled up, and it is skipped for now. And suppose that's all the emails that we have. Okay, so yeah, Selena asked, what if an email needs to be filed in folder 1? Yeah, that's a good question. It's similar like this example I've shown for folder 2, right? But in this example, I suppose that all the emails, only that one email, email 3 should be filed to folder 1. Okay, that's an assumption. So yeah, you just need to focus on this folder 2 for now. So okay, so now we move up, and so we have this we have this seventh email here at the bottom of the screen. Okay, so we just file it to folder 2. Since these are all the emails, we only have 7 emails. Okay, so after we file this F7, now the F1 will come back. Why? Because there are only 3 emails left, okay, on the right, and there are no more emails below. So the emails on the top will go back to the screen. Okay, so now we have like F1, F2, F4, and F6. So okay, so then it's quite straightforward. We just need to scroll down to and we have 6. Then we can file this first email and the second email to the 6th folder. Okay, and after that we just scroll down the folders, and now folders 7 and 8 are on the left, so we can file email 4 and email 6. Okay, so then we success. Okay, so how should we success? How should we find the optimal strategy? What's the optimal strategy? Actually, it's quite straightforward. So first, if some email on the screen can be filed, so you just file it, right? There's no hesitation. Because if you don't file it now, you may not be able to file it later. So the best strategy is just to file them whenever you can. Okay, but when there are not emails on the screen that can be filed to the correct folders, like we have seen that folder 2 case. Okay, so there are 2 options in this situation. Either we scroll the folders or we'll scroll the emails. So how do we choose? Well, one thing to be clear about is that there's no coming back to scroll folders, as we have seen, right? But there may be come back to scroll the emails, like we have seen. For example, if you have scroll all the way to the bottom, and you file one email, then the email on the top will come back. Okay. So, but it's risky. You don't know if it's possible like later. But compared with scrolling the folders, it's still a bit better because there may be come back. Okay, so if no other emails need to be filed into the top folder, like we have seen the folder 1 in the previous example, then we can safely scroll the folders because we don't need it right now. And we don't need it later. So we just scroll the folders. And otherwise, if there's some emails that need to file into the top folder, we are only left to scroll the emails, right? Okay, so that's basically the algorithm in this problem. It's quite simple, right? Yeah, and we can say that this is a greedy strategy. We only need to care about the current situation, and we don't need to care about like later. So that's not a dynamic programming. Okay, so now the algorithm is quite easy, but this problem, the difficulty of this problem lies mainly in the implementation. Okay, and how should we choose the data structures? How should we choose the how should we implement carefully to consider all the cases? Okay, so we need a fast way to make these decisions. So first of all, the folders on the screen are in a consecutive range, right? That's quite straightforward because like in the previous example, at first is from 1 to 4, and so we only need 2 endpoints of this range to know that which folders are on the screen. Okay, and for each folder, we can maintain a list of emails so that we can quickly answer the question whether there are other emails that need to be filed into the top folder. Okay, we can just maintain like for each email, we can, for example, in C++, we just have a vector. Okay, and the list of files on the screen knows that it may not be consecutive because we may have filed some email like in the middle, and yeah, and so we can use a set or a hash table. Okay, And that's the algorithm is just like this. We check the emails first. First, we check the emails from 1, 2, 3, 4 all the way to K, and file everything that we can have to the current folders on the screen. And after that, we are left with a bunch of emails that cannot be filed to the current folders. Okay, so so now we just need to make the decisions whether to scroll down the folders or scroll down the emails. So what we do is just check the top folder, and yeah, just as we described, the algorithm is quite simple, but the implementation you need to care about some details in order to consider all the cases. Okay, we have a bit time limit exceeded, so it's originally planned for like 1 hour, but it's now like 66 minutes. So I wish you don't be. I wish you are not annoyed by, this overlong presentation. Yeah. So if you have any questions, or if you think that some some code, if you find some code that you write have some problem but you can't find why, you may just contact me with this email. Yeah, any questions, and I'd be happy to answer for you. Okay, so yeah, that's it. I hope you can write your own program and get a pass, get accepted, like on USACO. Okay, thank you all. I guess that's the end of this tutorial.